Etna, and we can see this lava fountain with this tephra plume associated to it. So today's talk is going to take us following a format. I'm first just going to say a bit about buoyant plumes in general, and then introduce a bit further these tephra plumes that are coupled with lava fountains. And then I will talk about the application of a standard integral plume model to these plumes. After this, I will discuss the development and application of a new double integral plume model to these plumes. And then I will finish off discussing this case study of the 29th of August, 2011 eruption of Mount Etna, Italy. So first of all, why do we care about buoyant tephra plumes? Well, tephra plumes have a mechanism for which ash gets into the atmosphere. And once it gets into the atmosphere, it can pose a hazard to the wider region. It can damage people's vehicles as well as energy supplies, such as this damage to solar panels shown in this figure to the left. It can also block roads. And I can also talk from personal experience. You can also end up getting stranded at airports and international flight being disrupted, as I did in October last year. So now I'm just going to briefly just mention about the structure of buoyant tephra plumes in general. When a volcano erupts, all this hot material is ejected out, and it's initially denser than the surrounding atmosphere. It is initially momentum driven, and it's called the gaseous region. As this mixture is very turbulent, it entrains air from the surrounding fluid, and the buoyancy of the plume decreases to a point where the density of the plume is lower than the density of the atmosphere. In this region, buoyancy is the main driving force, and it's called the convective region. As it keeps entraining air, we get to a point where the density of the plume is equal to that density of the atmosphere, and this is called the neutral buoyancy height. Here, we get spreading occurring and the formation of an umbrella cloud. As the plume still has some momentum in it, we can also get overshooting of the top of the plume. So buoyant tephra plumes can be studied in a variety of ways. And one of these ways is by observations. Observations can be made from multiple different methods, such as using visible cameras, as shown on this figure on the left from ING for Catania again, where they're using a visible camera to be able to detect plume heights. Other methods include thermal cameras, satellite imagery, radar, as well as analysis of the fill deposits. Such observations include plume height, direction of plume spread, as well as the mass flow rate can also be inferred. So they can also be studied by modelling. There are many volcanic plume models out there and can range from simple 1D integral models all the way to more complex 3D models. And all volcanic plumes models can be used to look at the dynamics of plumes, as well as the source conditions with coupled to observations. So there's lots of ways to examine volcanic plumes. But the volcanic plumes I want to talk about today are those where the tephra plume is coupled to a lava fountain. And what I mean by this is when you have a lava fountain coexisting with a tephra plume. Here we once again have the example of the 29th of August 2011 eruption. And because this was taken during sunrise, we can see this incandescent region, which is the lava fountain, as well as this sustained tephra plume. At Mount Etna, these plumes have been known to reach up to 15 kilometers above sea level. But it's not only Mount Etna where they've happened. They've also been reported at Ishishima in Japan, as well as Eveanjelene. So today, what our objectives are is to determine if a standard integral model is applicable to such plumes, and if so, can they replicate the observations that we see from real eruptions? We then want to investigate the effect of the lava fountain on the plume rise itself, and we'll do this by using this new double plume integral model. And lastly, we want to apply this to a case study at Mount Etna to try and further understand the dynamics of these plumes. So starting off with the first objective, can we apply a standard integral model to tephra plumes that are coupled to lava fountains? So standard integral plume models source the conservation of mass, momentum, and heat flow, and are based on Morton 1956. They've got many assumptions, such as that the rate of entrainment into the plume is proportional to the characteristic velocity of the plume. It's from a maintained source. In addition, multiple adaptations have been made to such simple models to make them more applicable to volcanic plumes, such as the effects of by including the effects of particle fallout, as well as effects of considering the atmosphere around it, such as wind and humidity. Today, I will be using the standard integral model of the Guidan Bonadonna in 2012, and this plume does not have sedimentation, but it does consider the effect of wind on the plume rise. So let's jump in to looking at application of this model to Mount Etna. So the first thing we want to investigate with the standard integral model is looking at the relationship between the gas-flushed region and the lava fountain. We want to determine if there's any relationships or equivalences between the height of the lava fountain, the gas-flushed region, and the calculated ballistic height. And the reason why we want to do this is because there's been a bit of confusion about what is equivalent to each other and the relationship between these three heights. So I've listed the ballistic height here, and we will be comparing this to heights of the gas-flushed region and of the lava fountain itself. And to do this, we're going to use a Monte Carlo approach with the standard integral model. What this means is that we'll be running the buoyant plume model, in this case 500 times, over this parameter space with these different variables. And for each run in the Monte Carlo, we'll see, does it match our observations? And if so, what was the initial mass flow rate that resulted in that match? And that's what we're going to be looking at in the next slide. So here is our figure. On the x-axis, we have the simulation number. So this is the simulation in the Monte Carlo. As I said, we did 500. And then on the y-axis, we have height. We see that these blue dots here, these are the modeled plume height from the buoyant plume model of the runs of the simulations that resulted in the buoyant plume model matching our observations, which in this case was our observed height of 9 to 10 kilometers above sea level. For each of these successful runs, we've also plotted on the green dots. These green dots are the modeled gas-flushed region height from the standard integral model. And in addition, we've also calculated the ballistic height, which is using the initial velocity that resulted in that match of the standard integral model to the observations. And lastly, we've also plotted on these two lines. These are the observed lava fountain height, with the red being the maximum and the orange being the average. And these are taken from Calvary in 2018, where the height of the lava fountain was determined by looking at the thermal saturated region from thermal camera images. The first thing to note is that the height of the gas-flushed region, the green dots, is not equivalent to the height of the lava fountain or to the height of the ballistic the calculated ballistic height. So we now understand this lava fountain is something separate to, it's not the gas-flushed region of the plume. So we just wanted to clarify that point. The next thing we want to look at with the standard integral model is the mass flow rate determined from it. The mass flow rate for an eruption can be determined from multiple methods, including by using the plume height with empirical or numerical methods, as well as analysis from the field deposit. So we want to compare the mass flow rate from these two different methods. So here on the x-axis, we have the mass flow rate from the deposit. We've got these values from the literature for a number of eruptions at Mount Etna, Italy, for the plumes that are coupled with lava fountains. We have plotted these values against the mass flow rate derived from plume height using the standard integral plume model. And this was once again done by the Monte Carlo approach to determine the best mass flow rate matched with the observations of the plume height. We've also plotted on this dashed line, which is the one-to-one line, just to make it easier to compare. So what we can see is generally the mass flow rate from the plume height using the standard integral model is higher than that from the field deposit. While this could just be because of the field deposit looking at the whole range of the eruptions, and generally the height observations is taken just from like the climax, like the max point, so the highest height, these order of these differences is actually quite large. So we want to understand further, why do we have these discrepancies? And to do this, we have developed a new model. It's a double plume integral model, and we're going to be applying it to these eruptions to try and understand their dynamics further. So, as with all integral models, we solve the conservation of mass, momentum, and heat flow with an OD solver 45 in MATLAB. But in this case, we have two plumes. We have this inner cylindrical inner plume, which for us will be corresponding to the lava fountain. And this is surrounded by an annular shaped outer plume, which for us will correspond to the tephra plume. These two plumes are solved together and are coupled, and they can be coupled in more than one way. If we look here on the lower right-hand side, we see this schematic of the control volume, and I've put on some arrows here to show you what kind of coupling we can have. The first way these two plumes are coupled is by particle fallout. We can have material falling out of the inner plume to the outer plume, and then also from the outer plume to the surrounding fluid. They can also be coupled by entrainment, and we have three different directions of entrainment. We can have entrainment from the ambient to the outer plume, from the outer plume to the inner plume, and then also from the inner plume to the outer plume. So we solve these together, and they're both co-flowing, they're both going upwards, and we stop the double plume region when the velocity of the inner plume, our lava fountain, becomes close to zero, or if the solid mass flux rate inside of it becomes negligible. At this point, we transition to the single plume region, which is just like any other standard integral plume model from this point upwards. We do make some additional assumptions to those that are further to those of a standard integral model. And one of these is that the entrainment coefficient of gas from the inner plume to the outer plume, so this alpha value here, is set to 0. The reason why we do this is that we assume that we are not entraining anything really from the surrounding fluid. And this is kind of based on our observations. We see our radius of the lava fountain decreases with height, so we don't want to increase any of the mass flow rate inside of it. Secondly, we assume that the transition from the double plume region to the single plume region is instantaneous. And in terms of meteorology, we have no wind in this model at this point. We are using the standard atmospheric temperature and pressure profiles of Wood's 1988. We also assume there's no re-entrainment. So once a particle's fallen out of the inner plume, it can't be re-entrained, and the same can be said for the particles falling out of the outer plume. Here on the lower left, I have listed the entrainment coefficients that we use. You can see our alpha is set to 0. So this is the entrainment coefficient to define how much is going from the outer plume to the inner plume. And then the other two here are values taken from Bloomfield and Kerr 2000. Just a quick note on the source conditions of this model. The source conditions of the inner plume and outer plume can be set independently. And these include velocity, gas mass fraction, temperature, as well as a grain size distribution. And this goes back to the fact that because we have sedimentation, we need to know the sizes of what's in the plume. In relation to the initial mass flow rate, we say the initial mass flow rate is composed of what's inside the inner plume, as well as what's in the outer plume. And we define what's in the inner plume by this epsilon, by this partition coefficient. I now just want to jump back to what happens once this double plume region finishes. In some cases, we can still have some solid mass flow rate left inside of this inner plume. So we explore two end member scenarios to see what could happen with this material. The first one is what we're calling the moderately coupled scenario. And this is when, once this inner plume has stopped, anything inside of it is completely removed from the system. Secondly, what the second one we look at is the fully coupled scenario. In this case, we say anything that's in the lava fountain can be added to the surrounding plume and go into the single plume region if it can be supported by the plume based on the settling velocity and the velocity of the plume itself. So going on, I will be going back to these two scenarios just to explore the full range of potential options. So the first thing I want to examine with this new model is the effect of a lava fountain on the final height a tephra plume can reach. So to do this, I'm going to run the plume model 500 times for 3 different scenarios. First, for a tephra plume that does not have a lava fountain. And I will be modeling this with just the standard integral model. And then the next scenario is for a tephra plume that is coupled to a lava fountain in the moderately coupled scenario, so where anything in the top of the lava fountain is not added to the start of the single plume region. And this will be modeled with the double plume model. And then thirdly, with a tephra plume that is coupled to a lava fountain where it is fully coupled. And once again, we'll be using the double plume model to do this. In this table here are listed are the source parameters and the ranges we're exploring. But the only thing really important to know is that for the scenarios where the tephra plume have a lava fountain, the lava fountain is always going to be hotter, containing less natural gas, and be coarser than the surrounding tephra plume. So here are the results. On the x-axis, we have the initial mass flow rate. Just a note, when I'm talking about the double plume model, the initial mass flow rate refers to what's inside the inner plume, as well as what's out in the outer plume. And this is plotted against the plume height, so the final height the tephra plume reaches on the y-axis. And you can see we have our 3 different scenarios plotted. The black dots correspond to a tephra plume without a lava fountain, modeled with the standard integral model, while the colored dots refer to a tephra plume with a lava fountain, modeled with the double plume model, where the red is the fully coupled scenario and the blue is the moderately coupled scenario. And the first thing to note is that the tephra plumes that do contain a lava fountain do follow a similar trend and relationship between the initial mass flow rate and the plume height as those that do not contain a lava fountain. However, we can see that for a tephra plume that has a lava fountain, the variation in heights for a given initial mass flow rate is greater. One of the reasons for this is because of our new variables that we have. We can vary the size of the lava fountain as well as the grain size distribution. And I'm just going to focus now onto these 2 parameters further to explore the sensitivity of the inner plume to these. So the first thing we're going to look at is the grain size distribution of the inner plume and how varying that affects plume rise. So I'm going to start off with a lava fountain, so the inner plume, that only has a single grain size. And this is just for simplicity before moving on to a more realistic grain size distribution for the lava fountain. So for an eruption at sea level in a still atmosphere, where the initial temperature, gas mass fraction, velocity, and size of the lava fountain is kept constant, we're going to explore this plot here. So the only thing I'm varying is the grain size of the inner plume. And this is shown here on the x-axis, where it's in phi. So here we have the really coarse particles, and we go down to quite fine. On the y-axis is the final height the plume reaches. And you can see I have plotted 3 different results for 3 different sized eruptions defined by their initial mass flow rates. And we have a dotted black line, which is the results for a tephra plume that does not contain a lava fountain, modeled by the standard integral model. You can see this is a straight line because we don't have a grain size distribution in the, or a lava fountain in the standard interval model for a tephra plume without a lava fountain. And then you can see the colored lines, which once again correspond to a tephra plume that do contain a lava fountain, modeled with the double plume model, where the dashed red is a fully copper scenario and the solid blue is moderately copper scenario. So first of all, let's just have a look at the results when the grain size of the lava fountain or the inner plume is really coarse. And the first thing to notice is that there isn't a difference between the moderately coupled or fully coupled scenario. This is because these only, when the grain size is really coarse of the lava fountain, we have lots of sedimentation. It all falls out quite fast. So it means that once the lava fountain, the inner plume has stopped, there actually isn't anything left in it for it to go into the single plume region. So these two scenarios don't play a role. The second thing to note is that initially, a tephra plume that does contain a lava fountain is lower than that does not. As our grain size decreases in size, our plume with a lava fountain increases in height. The reason for this is because as our grain size distribution becomes finer, we have less sedimentation. So we're keeping more of this hot material inside the lava fountain. And as it falls out, it can go into the outer plume. So we're keeping more of this hot energy inside of it. If we look on the other side of this plot, we now see some variation between the two scenarios. So this is where the grain size is becoming quite fine. We see that the two scenarios, the moderately coupled and the fully coupled scenarios, are varying. And this signifies the point now where we still have some solid mass flow rate left inside the lava fountain once it has stopped. And let's first of all focus on the solid blue line. So this is the case where we have a tephra plume with a lava fountain that is moderately coupled. And we can see as the grain size becomes finer, the finer plume height decreases. This can be explained by the fact as our grain size is getting finer, we're having less sedimentation. So we have more material staying in the lava fountain. But because it's a moderately coupled scenario, none of this is added to the start of the single plume. So it's all just removed from the system. So the lava fountain is acting kind of like a sink. In contrast with the fully coupled scenario, this material now at the top of the lava fountain can be added to the start of the single plume region. And as a result, we're providing all this hot material to the surrounding tephra plume and it can go higher. And that's why we don't see so much of a change as the grain size becomes finer. So now let's have a look at the results where we have a more realistic grain size distribution in the inner plume in the lava fountain. So this time we've used a log normal grain size distribution where we've varied the medium grain size. So on our x-axis here, you can see we go from a coarser medium grain size to finer. These medium grain sizes correspond to these subplots here on the right, where you can see the medium grain size is defined in the boxes. We have our red grain size distribution is for the lava fountains, so the inner plume, and the blue is that of the surrounding tephra plume. You can see this one does not change. And then going back to this plot, once again on the y-axis, we have the final height of the plume. And once again, we have 3 different eruptions defined by 3 different sizes. And our 3 lines plotted for each one of these different eruption sizes, with the dotted black being a tephra plume without a lava fountain, modeled by the standard interval model, and the colored lines referring to a tephra plume that does have a lava fountain, modeled with the double plume model, where the red dash is a fully coupled scenario, and the blue solid line is a moderately coupled scenario. And we see the same as what we saw when we only had a single grain size composing the lava fountain. When the grain size distribution is coarse, we can see that there's no difference between the 2 scenarios of a tephra plume that has a lava fountain, and it's initially lower compared to those plumes that don't. However, as we become finer, we see that the final plume height rises until we get the divergence between the two scenarios, and we see for the tephra plume that's only moderately coupled to the lava fountain, we see the height decrease as our grain size becomes finer. So now let's move on and look at the dynamics of just two examples in a bit more detail. And to do this, we're going to take one set of dynamics for a plume where the grain size distribution of the lava fountain is finer. So this is going to be -3 phi in this case. And then one where it is coarser, defined by a log normal distribution of a median grain size of -7 phi. As before, the other source parameters are kept constant. You'll notice here only one scenario is plotted, and this is because we're looking in the double plume region. So as I said before, these two different coupling scenarios only comes into play once the lava fountain has stopped. So we're not actually at the point where these scenarios make a difference yet. So that's why I've only plotted one. So let's have a look at the figures on the left outlined by the green box test. And here we have the dynamic profiles of a plume where the grain size distribution of the inner plume is finer, defined by the -3 phi median grain size. And we have the profile of velocity with height, temperature with height, density with height, and the radius with height. And we have 3 lines plotted. We have the red dashed, which corresponds to the profile of the lava fountain or the inner plume. We have the blue, which is the profile of the surrounding tephra plume. And then we have the dotted black, which is the profile of just a plume with no lava fountain modeled by the standard integral plume model. You can see in this case that our velocity of the inner plume goes to 0 before the plume stops. And we can see also that the temperature of the inner plume of the lava fountain doesn't really change with height. And this is because we're not entraining anything into it. We can see our radius of the lava fountain also decreasing with height. And we can see how the density converges to the density of a solid particle. And this goes back to the entrainment. We don't have any entrainment into the inner plume. So because of this, all the gas has been entrained out, and we're left with just the solid particles. In contrast, however, if we look at an example where the grain size distribution of the lava fountain is coarser, this time it's defined by a medium grain size of -7 phi, we see a few differences. First of all, if we look at the velocity subplot, we can see that the velocity of the lava fountain doesn't reach 0. We've stopped the model before that because the solid mass flow rate in it is becoming negligible. We can once again see the radius of the lava fountain decreasing with height, and the lava fountain itself not really cooling significantly. However, this time, I just want to draw your focus to this line here, which is the profile of the surrounding tephra plume of the lava fountain. So with this surrounding tephra plume, we can actually see that the initial temperature initially increases before decreasing again. And the reason for this is because we have this really high fallout, because the grain size is really quite coarse, a lot of this goes into the outer plume, heating it up. So we can actually see the lava fountain affecting the surrounding tephra plume. I also just want to bring your attention to the density profile of the lava fountain here in this red line, in this bottom right-hand plot. And we can see initially the density of the lava fountain increases. And this is because we have a lot of entrainment out with it as the velocity is high. So we're losing gas and have more of the solid. However, we see a point where we end up having a lot of really quite high particle fallout as well, still going on, and the rate of entrainment slowing down. So we see the density decreasing. This here is just an artifact of the model due to the size of the width of the lava fountain becoming smaller than the particle size in the plume. So another parameter I want to bring your attention to is the size of the lava fountain. Does changing the size of the lava fountain have different effects on the plume? So to do this, we're going to take a similar approach as before. We're going to look at this hypothetical eruption at sea level in a still atmosphere, where the initial temperature, gas mass fraction, velocity, and in this time, grain size distribution is kept the same. So we're just varying this epsilon, which is this partition coefficient. So this is how much of the initial mass flow rate in the double plume are we putting into the inner plume. So the more initial mass flow we put into the inner plume, we're saying the larger the lava fountain. And we're going to look at this for two different examples. Once again, when the grain size of the lava fountain is finer, and another where it is coarser. So first, let's have a look at where it is finer. And once again, we're defining finer as by having a log normal distribution where the medium grain size is -3.5. On the x-axis, we have this ratio of initial mass flux rate partitioned into the inner plume. So the larger this ratio, the more the initial mass flux rate put into the inner plume, so the larger the lava fountain. And this is plotted against the final height the surrounding plume reaches, or the single tephra plume. Once again, we have three different eruption sizes we're exploring. And we have three different lines for each of these different eruption sizes, where the dotted black line corresponds to a tephra plume without a lava fountain, modeled by the standard interval model, which you can see is once again straight, is because it's not sensitive to the size of the lava fountain since it doesn't exist in this case. And then the colored lines to the case where we have a tephra plume coupled with a lava fountain, where blue is a moderately coupled scenario and the dashed red is a fully coupled scenario. And what we can see is as the lava fountain gets bigger, so as we put more of the initial mass flow rate into the inner plume, the final height the plume can reach increases. And this is because the grain size distribution is quite fine, anything that falls out can be added to the surrounding plume or can go into the start of the single plume. So the more of this material we have, because it's more hotter than the surrounding tephra plume, we have more like energy associated with it. So we can make our plume go higher. In contrast, when the grain size distribution is coarser, defined this time by medium grain size of -7.5, we see the opposite trend. So this plot is the same before with the ratio of initial mass flow rate on the x-axis and the plume height on the y-axis. And we've got the three different eruptions sizes. And you can see there's no difference between the two scenarios of this coupling between the tephra plume and the lava fountain that we are exploring. And this is because, as I've said before, because it's coarse, there's nothing actually left in the top of the lava fountain to actually potentially add to the start of the surrounding plume. So these scenarios are not important for this example. But what we can see for both these scenarios is initially our height of the tephra plume with a lava fountain is higher than that without. But as the lava fountain gets larger, the final plume height decreases. The reason for this is because even though we have more material that's hotter in the plume in this lava fountain, because it is so coarse, it's not supported when it sediments out to the surrounding plume, and it can't be, so as a result, it's kind of like acting as like a sink. Everything's falling out of it and it's not really playing too much of a role with the tephra plume. So now I'd like to move on to this case study. And the case study I'm going to look at is this eruption from the 29th of August 2011 at Mount Etna, Italy. So here is a video, courtesy of Eveanjelene Snee, of this eruption. It happened at sunrise, so we can once again see this incandescent region of the lava fountain. There's been lots of observations of this plume, and this is one of the reasons why we chose this case study to look at first. So this plume had an observed average plume height of 9 kilometers above sea level, and it had a maximum observed height of 9.6 kilometers above sea level. The height of the lava fountain has been reported as an average height of 453 meters above sea level, to a maximum height of just over a kilometer above sea level. In addition to this, the fill deposit has been analysed and a mass flow rate has been determined from it. And we're going to call this the wider fill deposit mass flow rate. The reason why I'm just giving this a separate name to begin with is because with these eruptions, they form quite a prominent cone deposit at the top of the volcano. And a lot of the material that falls out of the plume and lava fountain go into this cone deposit. The area I'm talking about is hundreds of meters from the vent. So generally, this isn't characterized in wider fill deposit analysis. However, estimates of the erupted volume in this cone deposit are reported in Beckner 2014 and Eveanjelene 2018. So from these estimates of the volume in the cone, we have estimated the initial mass flow rate, the mass flow rate associated with this erupted material. And we've added this to the mass flow rate determined in the literature from the wider fill deposit. And then this total, we're calling this total estimated fill deposit. So this is everything in the cone, as well as everything elsewhere. So to look at this eruption with a double plume model, we're once again going to use a Monte Carlo approach. And this time, we're going to use the observations of the final plume height, as well as the height of the lava fountain. So we're trying to match the final height of the surrounding tephra plume to the top of the single plume model, and then the height of the double plume region to those of the lava fountain. We're always going to make sure the lava fountain is hotter and contains less initial gas than the surrounding tephra plume. And the standard integral plume model will also be used for comparison, and its initial source parameters are the same as those of the outer plume. In terms of the grain size distributions we use, I've plotted them here on this plot on the upper right. So we have grain size on the x-axis and the weight percentage on the y-axis. This black line, grain size distribution, is the total grain size distribution from the 1959 Kilauea Iki eruption. And we'll be using this for the grain size distribution of the inner plume. The reason why we're using this is because we would really want this to capture the really coarse material close to the vent, as this grain size distribution does. At Etna, the grain size distribution of the cone deposit hasn't really been analysed, so we thought it would be best to use one from a different volcano that has captured this really coarse material. For the grain size distribution of the outer plume, we'll be using the two different ones. The first one in red, which is just from the analysis of the field data. And then the second one in green, which includes some synthetic data to compensate for the lack of medial data. So let's have a look at the results for just the tools we would have before this new integral model. On the x-axis, we have the mass flow rate. And then on the y-axis, we have the final plume height of the tephra plume. You can see the range is just between 9 and 9.9 kilometers, because this is the range of observations of the final plume height of the tephra plume. I've plotted here this yellow bar, which is this wider fill deposit mass flow rate estimate. So this is the estimate of just from the fill deposit analysis. Along with this, I've plotted these black dots, which is the mass flow rate estimate from the standard integral model when it's being constrained with the observations of just the final plume height. So this 9 to 9.9 kilometers above sea level. And we can see this discrepancy for all the different height ranges between the mass flow rate estimate from the model to that of the fill deposit analysis. If we then plot on this total estimated fill mass flow rate, so this is the mass flow rate from the fill deposit, as well as our estimate from the literature of the material composing the cone deposit, we can see that this value is more comparable to the mass flow rate determined from the standard interval model. So these are kind of agreeing with what's coming actually out of the event. However, it doesn't actually tell us at the moment anything about what this wider field deposit mass flow rate correlates to. And to explore this further, we will be using the double plume model. So this figure here on the left is the same as before. We have mass flow rate on the x-axis, and on the y-axis, our final plume height of the tephra plume. We have our field data points estimated, the yellow line and the purple line, as well as the black dots for the standard interval model estimate of the mass flow rate. Now there, we also have all this additional data from the double plume model. And I'm just going to start off with the colored dots. What these are is the mass flow rate estimate from the double plume model when we're constraining it with the lava fountain height observations and the final tephra plume height observations. And it's for the source. So what's coming out at the vent? So what do we start off with? The different colors refer to the different grain size distributions used for the outer plume. So the one that has the synthetic data, the one that doesn't. And you can see it plays no real role. It's quite similar. So at least we know we're not too sensitive to this parameter. And these are also quite comparable to the estimate of mass flow rate from the standard integral model, as well as the one we've estimated based on the literature values for this total estimated field mass flow rate. However, because we have sedimentation in this double plume model, the mass flow rate of our solid material varies as we go upwards, because we have quite a lot of sedimentation happening. So we've also plotted on the mass flow rate estimates of the solid material at 3 different heights. So at the start of the single plume, which is shown in the circles, also at the neutral buoyancy level, shown by the squares, and then also at the top of the buoyant plume itself, shown by the stars. And what we can see is that the solid mass flow rate at these heights are more comparable to this mass flow rate derived just from the field deposit, this wider field deposit. Another thing to notice is that the change between the mass flow rate estimate of the cone and the field to just what's off the field can also be reproduced by the plume model. So if we say this is the total estimated field mass flow rate is estimating what's being erupted at the source, we can see this corresponds well with the color dots from what the double plume model is telling us is erupted from the source. So we're getting this change of solid mass flow rate with this model as well. But which height this wider mass flow rate corresponds to within the plume is dependent on which height range we're looking at. If you look at the higher height range, we can see it could correlate to what's actually at the start of the single plume, or what's at in the neutral buoyancy level. While if we're looking at the lower height range, we can see it's probably more likely to be what's at the start of the single plume. So once the lava fountain is finished, what's actually going into the buoyant plume itself. So that sums it up for me. I just want to conclude that we've clarified the lava fountain. Lava fountain is not the gaseous region of the tephra plume, and that lava fountains can affect buoyant plumes, but the extent of the effect is dependent on the source conditions and how big of a lava fountain we have. We've also further explored the discrepancy of the mass flow rate estimates from 2 different methods, from the plume height and from the field deposit. And by using the double plume model, we can actually explore these differences and explain why they are there. However, further quantification of the source parameters, which we could use in the double plume model, are required. And there's also further things we could do, such as the inclusion of wind and thermal equilibrium in the new double plume model, which would help us explore the effects these process it would also have on the coupling of the tephra plume to a lava fountain. So yeah, thank you.
Thank you, Evie. That was fantastic. We do have time for some discussion and questions, and I see there are a lot of questions and discussion points in the chat. But if you'd also like to just raise your hand and ask a question live, you can do that. What I'm going to try to do is interleave those sort of live questions with some of the chat questions. And I see there's definitely some common themes in the chat questions. So I'm going to try to kind of pick these to encompass most of the discussion. But if you feel like I've left something out, or if you want to add to it, please feel free to unmute yourself and add to that question. So I'm going to start right now, I guess, with a question from Larry Maston. And the question is about heat transfer, and how is heat transfer from particles to the gas considered? I think you alluded to that in the last point there. Do you assume a thermal relaxation time? Do you assume perfect thermal coupling between the particles and gas?
Oh yeah, so at the moment we're not considering any disequilibrium. It is something we want to do in the future. And we're looking at the work of Woods to start this off by using potentially just like a coefficient estimate to begin with, but it's definitely something we do need to think about and something I will be looking at. Sorry, I can't give more detail at this point.
No, that's great. And so I think a very much related question is, do you, when you're looking at the heights, basically where you go to the single plume model, is that set basically then by the entrainment coefficients then that you specify?
So the height, sorry, can you just repeat that?
Or is that height dynamic, I guess is what I'm asking. Is that?
So the height of the double plume region, yeah, so that will vary depending on, basically it can equate to our ballistic height if we don't stop before we've actually run out of material inside the lava fountain. Because we have such a coarse grain size distribution in some cases, we have really high sedimentation, so we're left with just the gas phase in the lava fountain. So our height of the double plume region, our lava fountain, is variable on how much initial momentum and also how fast things are falling out of the lava fountain itself.
Right. I think this, Ben, you can correct me, Ben Andrews asked, I think, basically this question. So if you want to follow up on that, Ben, let me know. And I saw Larry maybe had a follow-up question too.
No, I was just trying to show my face while I was listening to the answer.
Okay, okay.
But well, I guess now that I have the floor, so it sounds like you're basically taking the thermal content of the particles out of the system once they decouple from the plume. Is that right? Yeah,
like if things fall out of the inner plume and is added to the outer plume, we determine if, okay, is it supported based on the velocities, and if not, we just remove it from the system.
Okay. Yep.
All right. We have a number of questions that are kind of in this theme. So, and so the folks asking these questions can certainly unmute themselves and add to this discussion. This is very much related though, Evie, and so you may have basically answered this, but this is from Mark Jelinek. At what height above the fountain, how many fountain heights, is it reasonable to define a source buoyancy flux for a 1D Morton-Taylor-Turner style model?
Sorry, could you repeat that, please?
Sure, yeah, I'm sorry, it's tricky. So at what height above the fountain, so how many fountain heights? Is it reasonable to define a source buoyancy flux for just a 1D kind of Morton-Taylor-Turner, I guess he's referring to a kind of classic style integral model, so single model. Is that
yeah,
right?
So please correct me if I'm answering this wrong, but the way we're doing it, we just do the one height, and it is based on a lot of assumptions, just try and simplify the problem. It's probably best if I get back to you at a later date, though, whoever asked that question, for a more in-depth answer than I'm giving right now.
Oh, absolutely, and I should say, Evie, that we're recording all the chat questions, so you can always do later too. So, all right, so this, okay, many of these are very similar themed, but that's okay. Greg Valentine is asking how the results would compare to a single plume model where the dusty gas mixture of the plume, so the gas plus particle mixture that is in thermal equilibrium, is defined by the total eruptive gas content but only the low Stokes number. So basically, if you only had fines, and I think you have some comparison you can even refer to, right, for this?
Yeah, so what we do is compare to a standard integral model where we do just have no sedimentation, basically. So just everything's together. We don't have any fallout, so we've got this dusty gas. It will also be actually interesting to compare to a standard integral plume model that does have particle sedimentation and see what kind of relationships we're seeing then and what kind of discrepancies we're seeing for with a tephra plume, with a lava fountain, so those that don't have one. As I said, there's loads of volcanic plume models out there, and they've all got these different processes they consider. So we should also look at ones that consider additional processes, because as you're right, at the moment we're just looking for one that everything's just together and mixed, and basically you can correlate that to just having loads of fine material in it.
So Yoshi is asking, this is more about data. So is there thermal or Doppler radar data available to help constrain ESPs, similar to Valentine's previous work on MER from Volcanology at Etna? So Yoshi, add to that if you need to.
Yeah, just I know Valentine that who's working with you has done some previous estimates with the Volcanology. So just wondering if you use that data to help constrain source velocities and perhaps even measured MERs derived from radar data in situ.
Thank you for the question. So what we do, not in this work, but in the following work we've been doing since we've done this, is that we've used the radar data to try and constrain how much of the initial mass flow rate is inside the lava fountain itself, so inside this inner plume, under the assumption the radar's just really seeing this coarse material. And then we're using this value to look at loads of different case studies we can, because we've managed to constrain one of these 3 parameters. So this work is still ongoing, but yeah, it's definitely great to use all this other data that is out there, because we don't really know the source parameters and what they should be.
And then just to follow up on that, the radar that they have there, I'm assuming it's still Volcanology, the 23 centimeter wavelength. So basically imaging relatively coarse particles, like you said. Can it scan, or is it just aimed at the source or the lava fountain?
I don't think I'm the best person to answer that question, I'm sorry. But
that's all right, I'll ask Valentine.
Yeah, ask Valentine. I'm sure he can give you a lot better answer than I could do at the moment.
That's fine, thanks.
Well, excellent. Evie, that was a great talk. We're kind of out of our end of our hour here, but if you're okay sticking around for a couple more minutes, we can all thank you, of course, but then for the few folks that want to ask one last question that we didn't get to, go ahead and stick around for a little bit. And please join us again next week. We'll hear about Costa Rican volcanism.
Actually, if we're sticking around, I guess I have another question, Evie. So early in your talk, you showed a plot with observed plume heights and estimated